Okay, hello. Welcome to third year Analogue Electronics. First thing I should say about this course is it's a bit of a misnomer really. Not really about analog electronics per se, but more about the analog aspects and other production and practical aspects of building circuits, ironically, particularly to do with digital circuits. So I'm Dr. Steve Wright, and this is a series of videos that I'm going to make for each of the lectures in this course, 5 or 6 of them, as we'll discuss. And these will be posted on Blackboard to help with your revision or to go back over any lectures you might have missed. But I would stress, please don't use this facility as a substitute for lectures, because there can well be information that will be in the main lectures that aren't in these videos. And so the lectures might be updated as well between the videos and the actual lectures. So regard this as a backup facility rather than a substitute. But I hope you'll find it useful. And I should also say that if you do find it useful, can you also send me an email to say that you've been using it, because I just want to get a feel for how many people are using it and whether it's useful. Don't want to waste my time making these videos if nobody's bothering with them. So please drop me a line and I'll tell you how to do that in a second. So, hello, this is me. I'll be helping Nigel Gunton offer this course. I'm Dr. Steve Wright. And a bit of housekeeping first. You can see you can find me in N block 2N30. That's my phone, but my email is probably the best way to get in touch with me, steve.wright@ui.act.uk. So any questions, please drop me a line or come by the office to find me. Very, very happy to answer questions or talk things over, because it gives me a feel for feedback about the course, how people are getting on with it, things that could be improved and whatnot. So please get in touch, any questions. So a little bit of background about myself. I'm new here to UI. I was originally a student I did my bachelor's at Birmingham University, as you can see, in the late 80s. And I did electrical and electronic engineering, very similar to what you guys are doing here now. And so you can see I followed a career path, which I hope a lot of you guys will as well. Mainly in aerospace, but very much electronics within aerospace. So I spent 8 years in Derby at Rolls-Royce doing some fabulous projects there to do with engine control systems and monitoring systems and whatnot. Then I moved to Bristol and had a sabbatical in the silicon industry, ST Microelectronics, no longer there now, but up at Aztec West up the road, working on microprocessor development. So very much what we'll be talking about during this course. And then back to aerospace for me, working on all sorts of avionics projects. So my main role here at the university is avionics particularly, but obviously this requires a deep understanding of the electronics that compose that. So here in Bristol, I went back to university to do a doctorate a couple of years ago, and I joined UI here at the end of last year. Very happy to be here and looking forward to sharing some of my experience with you guys. So there's 1989, my final year project, in a mixture of analog and electronics. Just got my mixed system to work. As you can see, I'm rather pleased about it. So the point I'm trying to make here is I feel your pain when your final year projects are refusing to wake up and dance. Yeah, been there, done that. So yeah, then at Rolls-Royce did all sorts of design here. So all the different aspects of building and operating a piece of electronics and software to support it. That particular one was at Rolls-Royce, as it happens. And then I'm not just here to bang on about my CV, but also to point out what the point of all this is, and I hope what you'll end up doing with your careers. So here, what we see here are what they call system integration benches, avionics test rigs by any other name, This particular one is the A380 up at Filton, a fuel avionics system there, which I spent a lot of time developing and operating with the guys that you see in the picture. So a huge amount of electronics to simulate all the analog aspects of an aircraft and interface them to the digital avionics systems that control them. So I think you'll see a very good basis of what we're going to be talking about in this course. So a nice little anecdote here is that this fabulous system here, one day we came in to do some A380 testing and nothing worked. Ended up pulling the computers to bits, trying to find out where on earth it had failed. For a few hours we found this connector had been chewed through by a mouse and brought the entire A380 test program to a juddering halt. So that's exactly the sort of issue that we'll be looking at in this course, I think. So various electronics and an evolution I want to show you about that I've been involved in and over the years. And the point I want to make with this particular slide is there's been an increase in complexity over the 20 years I've been working in the industry, and also a lot of escalation from a component level development that's through to a sort of pre-packaged system like this, very much off-the-shelf devices like that, which then are modified in software, and that's been true. So it might, at first you might start to think, well, what's the point of spending my time on electronics, deep down electronics, where we're sort of studying these components here. Oops, I'll just use the individual components on the board here. This particular microprocessor with the Hitachi thing that I was involved in the late 90s. But I think it's very relevant because somebody's got to design those for starters, but also I'm rather hoping that in the next few years there'll be something of a back to basics campaign with all these fabulous systems that we've seen coming out lately, the Raspberry Pi and even simpler versions of these very, very cheap electronics. And I think this is an excellent development that's come along in the last few years. The Raspberry Pi seems to have kicked it all off, and now there are a whole load of Me Too systems as well. Originally designed for hobbyists and school children, but the number of commercial enterprises out there are actually using these devices is quite remarkable. A lot of people using them, and I think this is great because this keeps alive, and it requires a knowledge of how these electronics work and the sort of a deeper understanding of what these machines do and how they can fail as well. And so I think this is where this course will be highly relevant in a world populated with this sort of equipment. And so I hope there'll be all sorts of interesting projects out there for you to play with. Now, here's the, just want to talk about the course itself. Here's the learning outcomes. Don't worry, I haven't read it all in its entirety either. This is the course specification, so you're very welcome to download this. I should stress that all the slides are available. I'll tell you where in a moment. So this is where we want the course to go, but just to boil it down properly, let's just translate that to what I really want to tell you about. What this course is going to be, it's not really analog electronics per se, but that electronics is to some extent still a black art, and there are various effects that can be exploited, but more often than not will be there to trip you up, and a basic understanding of what those effects can be. And also, when we plug things together, if it's of any level of difficulty that's worth looking at, they don't work at first. So we need to debug our systems as well. So I want to teach you guys in this course about all the things that can go wrong and all the things that can go right, and all those tricks of the trade and all the tools, because that's what a good engineer does. He knows the tools and the techniques that are available. He knows the people to ask. And so this course is trying to give you that understanding. When I started in electronics and digital electronics especially, it's very easy to think of everything just switching on and off and being perfect the whole time. Things go wrong all the time for various reasons, and I want to explore those reasons to give you guys a head start when you do your projects. So with that in mind, most of this course is coursework in the lab, but we want to have a few lectures thrown in for you to support that work and help you along. And so at the moment I'm planning 5 lectures, one of which is this one. So here are the titles, and I'll give you a bit of detail about them in a minute. So next week we'll be talking about analog issues. So what do I mean by analog issues? Well, these are all the funny electrical issues that occur particularly in digital circuits, or it can happen obviously in analog as well, but they do happen in digital circuits that people don't tend to think about. And so we want to put that in context and give you a heads up on all the various things that are out there ready to trick you. As circuits get faster and faster, the issue of interference, which is where electrical signals start interacting with each other unexpectedly, and as I say, as circuits get faster, particularly in off-the-shelf consumer electronics and things like that, these interference effects become more and more significant. And so I wanted to have a whole lecture just talking about that. And also, if you're designing electronics for sale, you need to demonstrate that your equipment is fit for sale. And interference and interference compatibility is very much part of that in the modern world. So yeah, we'll cover that in some detail. Then I want to talk about tools and testing and debugging of circuits. So debugging when we develop a circuit or a piece of software or a system containing a bit of both. We usually switch it on and nothing works. So how do we go around taking it from there? We don't just throw up our hands and give up. We press on, we debug it. I hope that I'm telling you things you already know at this point, but it's very important to restate the case in context. And so we're going to have a lecture on debug tools and methods.
Cheers, John. Cheers.
Production of PCBs and populating them with components and things like that, and connectors, the actual mechanical devices that implement electronic circuits. It's quite a big deal. It's very easy to sit down in front of a CAD machine and design your electronic circuits and forget about all the various production issues that come up. And so I want to talk about that in one lecture. And this is a particularly interesting bullet here. This is something that's come up in the last few years, in that the world is filling up with all these poisonous electronics, and now there are a lot of regulations out there on how to dispose of them. So I want to talk about that, and how we can design our components with a pre-thought out life cycle, and how we can design our components for easy disposal, as well as all the other effects that we have to consider when we design. I'm going to leave a slot open as well for whatever comes up. I'm interested in your feedback in this course to find out which of the bits you're finding hard, which of the bits aren't clear, things that you think are missing that you'd like to hear more about. So please keep me informed, all the different thoughts, various thoughts about things you might want to hear about. So that lecture hasn't been written yet, so I'm interested to hear on what you think might be appropriate, or whether an actual lecture is needed at all. So please keep me informed on that, and we'll talk about that later. I should also say this video, I hope you found it here on Blackboard, and all the slides will be posted under the learning materials directory on Blackboard. And I will keep directing you to that. And during revision, or if you need to do something, I would encourage you to look at those slides again, watch this video again, things like that. This is going to be something I want to talk about when there's an audience in front of me. I also want to get a feel for the experience that you already bring to the party. You're in the third year now, and so one of the bits of experience that I'm lacking is an understanding of what experience you have. So I want to talk to you about what you already know. So I'm not patronising you too much, but similarly not going on about things that you don't necessarily know about. So we'll talk about that when we're all together. So with that, I want to go back and I want to reinforce the point about all the things we'll be talking about. And the key point I think I want to make in this and most of the lectures is that it's very easy to think of digital and analog electronics as two very different worlds. And it's also very easy to think of digital, because it's so ubiquitous in our world, we've all got digital electronics in our pockets. It's very easy to think of digital as somehow being better. But again, there's analog electronics in this, and by the same token, digital electronics is itself analog, and I want to qualify that in a second. So again, this should be pretty obvious to you, but statement again of what is analog electronics and what's digital as we think about it. And essentially it's the way that we transmit information, whether it be between circuits or actually within circuits as well. Analog electronics, the information is proportional to the magnitude of a continuously variable voltage or current. So in other words, the number of electrons that are pushing or flowing through that circuit represents the information. Digital information is all of, obviously, about a combination of different voltages. So that can be in time, in this case, of this thing switching on and off in a serial link, or we can have multiple pieces of wire, all with one on-off signals coming down them. But the point is that it's about a combinatorial thing. And so, again, restatement of the obvious, but it's important to bear that in mind. So digital electronics, hugely successful approach to information processing. And there's so many good reasons why digital is a very good way. And I think the key party trick with digital electronics is this capability here. And that is where inevitably signals will become polluted with noise. Now, where that in an analog signal, that noise will tend to build up and up and up. In digital, it's possible to throw away that noise and regenerate and reconstitute the signal as it passes from one area to another. And that's a very important party trick. It also allows us to do some extremely complicated functionality on that signal. I mean, we're all used to an AM radio, maybe you're not in the newer world. But the key point is usually software and hardware at the digital level allow us to do some extremely complex processing, which would be quite difficult to do. It's usually done in software, but hardware, in the case of these field programmable gate arrays and things like that, and so programmable logic also makes that possible without software. And I think those 2 points probably underline the reason why digital electronics has become so successful in our world. But it's important to understand about analog as well, because analog's still out there. I mean, as I say, the front end of the analog signal that picks up my phone signal, it's an analog device picking that up and feeding it to the computer, which then does the digital signal processing. So it's important to realise that analog is better in some ways. I mean, it can be done very, very quickly. Processing and amplification. It's a multiplication effect, really. And we can certainly multiply two analog signals together a lot faster than even the fastest processor can do. And also, analog degrades more gracefully. What do I mean by that? And I'll explain what I mean in a minute by showing you how badly digital systems degrade. It means that if we get a small amount of noise on an analog signal, that corrupts the signal, but probably not by very much. The basic number that's there is usually good enough in order for the system to remain working. And that's why it took a long, long time for things like digital electronics to make their way into safety critical systems. So if you came to my avionics lecture, you will discover all the ways that avionics has to defend against the issues with digital electronics. The other thing to bear in mind is analog is also, in principle, albeit not necessarily in practice, infinitely precise. There's an infinite number of different voltages that an analog signal could take, or currents I should stress. And in reality, noise means that there's a certain best resolution that's achievable, but in a very good circuit it's got a very smooth response, whereas digital interpretation of information results in this step response, which can have its own issues. So it's a form of noise. So I want to talk about where this apparently perfect digital world starts to break down, and the sort of things that you need to think about when you design your digital systems. At the very top level, this is a slide I often use, talking about a microprocessor. We always think at a very architectural level about the contents of a microprocessor, and we have pretty boxes and show information flowing, and we talk about very abstract concepts like program counter registers to show where we are in the software and things like that, and fetching data. But it's important to understand that within that chip that implements that microprocessor, everything's pretty much made up of a particular logic gate called a NAND gate, and I hope that you're familiar with this. And the NAND gate is interesting because you can make pretty much any logical device, and you can store information, you can process information, you can make programmable logic as well, all out of NAND gates. So that's the next level down in that block diagram that we just showed you, your microprocessor or any other piece of sophisticated logic in the digital world. But it doesn't stop there, because under the hood, the NAND gate is itself simply made of transistors. And those transistors are themselves made up using these doped silicon crystals, effectively. Now, that could be a whole course in itself. I understood for one perfect night before my semiconductor exam how those systems work, but for the purposes of what we're talking about in this course, I'm going to stop there, and I'm just going to say, right, we have transistors that are made up using this CMOS process, which implements these field effect transistors. There are other ones as well, but as you're probably aware, CMOS is the process which dominates pretty much all the devices in our world today. So our pockets are full of CMOS devices hammering away. So let me just fill in what CMOS and MOSFETs are. You'll notice this blue highlighting here. And so one of the standards I'm going to try and use in these lectures is wherever I introduce a bit of jargon like that, I'll try and throw it into a jargon buster here to explain what that is. Now, I'm not expecting you to learn the exact words of all that, but I just want you to take on, when I see a jargon buster, what that information is and what the basic meaning of the information. I don't need parrots so you can recite back the exact words, but tell me what it means. So I'll try and throw those jargon busters in, and if I've inadvertently put some jargon in that perhaps hasn't been covered properly, please get back to me, and I'm very keen to update these slides with extra jargon busters if you feel there's something missing. So that's CMOS. It's out there, and through a series of different levels that we've just looked at, it underpins all these devices that are out there. And so the point I want to make in this slide here is to give an example of how these aren't just electronic devices, they are analog devices. They just switch on and off using some pretty basic physics, quite complex physics in some ways. And so, but because of that, they can go wrong in often quite unexpected ways. So the particular example I'm showing here in this slide is a thing called a single event failure. It's a big problem in avionics because when you fly into the upper atmosphere, there's a lot of high energy particles flying around, which can come drilling through our devices and accidentally switch them on. So in this instance here, we can accidentally cause a bunch of ions to form in the substrate of this CMOS device that composes our computer, and it might inadvertently switch on that gate. And that can cause a glitch where a piece of data suddenly changes from a 0 to a 1, or worse than that, it can cause a permanent damage to the device by switching two gates on simultaneously. It shouldn't be, and causing permanent damage to the gate or something like that. Although this is a relatively corner case in consumer electronics, in avionics this is quite a big deal, but the point stands for all sorts of interference. So we'll be talking about this in the interference lecture next time at 1. So there's a good example of how this stuff goes wrong, because and it becomes obvious it's going to go wrong if one holds in one's mind, in the back of one's mind, the basic principles that create these technologies. So just to state the obvious over and over, digital electronics is under the hood analog. So you can see here there's this apparently digital signal switches on and off. We can get noise on that signal, and as we established in that previous slide, we can get rid of that noise again by switching, but if the noise is too great, it can corrupt the data very badly, and we can corrupt that information. And when it does corrupt, it can corrupt catastrophically. And let's look at that, because the key point here is, look, as we showed how analog information degrades gracefully, if we set a single bit the wrong way because a piece of noise has corrupted that across the threshold, and the information degrades very, very quickly to completely random numbers. It doesn't just degrade by small amounts. And so for a lot of systems that can be disastrous. So a good way to think about it is digital systems and the data stored in them, the information is very fragile. So in other words, it doesn't break, it's quite brittle. It doesn't break very easily, but when it breaks, it tends to break very catastrophically. So that's one of the key differences between analog and digital systems. So if data's bad, when you actually get to the instructions that are stored inside a computer program, the software is itself stored in hardware, of course it is. And here, the problem is amplified even more, because we might have an instruction set, an instruction which is just a bunch of ones and noughts in memory that causes a particular operation to happen in our microprocessor. But here the problem happens in spades, because if we corrupt that bit there, we can have a completely different instruction, and that will generally cause the program to crash or behave in an utterly unexpected manner. So again, this point about a brittle system that does not degrade gracefully. And there are methods by which we can defend against this brittleness, this fragility of digital systems. So that's at an electrical level. We also want to think about how all these systems are not only analog systems, they're mechanical systems as well. They've got physical devices sitting there. And it's very easy to overlook that because there's no moving parts. But these parts do degrade, and they do go wrong. And especially when they're in the real world. This one sat in my pocket. And so all sorts of things can happen. This one rather amuses me, in that that's a special kind of mold that lives on PCBs. How about that? This is a microscopic crack in the via, in a pin poking through a PCB, which can cause some extremely unexpected failures. And they can happen for all sorts of different reasons. And then it gets worse when you start trying to plug circuits together, because maybe you've discovered this already in your year's study so far, but connectors are often the electrical engineer's enemy, and they are particularly prone to causing disaster. In my experience in electronics, when something goes wrong, the first thing you do is check all the connectors. We all know that. Is it plugged in at the wall? Is the socket thoroughly pushed into our device? Is it working? And when things break, they break badly. And often when things are out in the field being used, they can cause all sorts of failures to occur. And when connectors can degrade quite subtly if a pin gets pushed back or something like that. So another example of how the mechanical world encroaches on our apparently perfect digital electronics world. And you can't overlook that when you're designing your stuff. So that's the end of this first introduction. Just to sum up, let's just look at that again. We always think about digital electronics as just switching ones and noughts, and that's a very convenient abstraction that we make. And the ones and noughts go to make these digital numbers, which are apparently perfect and never go wrong. In reality, that's not true. These digital circuits are, for the fear of stating the obvious, they are analog circuits under the hood. And those analog circuits are nothing but devices switching streams of electrons on and off. And as anybody who's done their physics A level, physics O level will understand, electrons whizzing along cause all sorts of strange effects. It's not like water pouring down a pipe, and a lot of those effects can be unexpected and often undesirable. So we have to maintain an understanding of what these systems do and what those effects can be. And then finally, this point about although the virtual world, and we always talk about the virtual world, seems very abstract and disconnected from the real world. These devices are ultimately mechanical devices. They're mechanical artifacts. And although they have no moving parts, they still break. It's very easy to think of them as just things that sit there, not moving and hence not breaking. Not true. And we must think about that when we design and we debug and we develop. So that sets us up for the course, and look forward to seeing you in the labs and working with you on all this. See you next time for Analog Effects. Here's the invitation for questions, so please give me an email if there are any questions.